In this video, we are going to walk you through the process of imposing a design constraint on the strains of a composite laminate. My name is Christian. If you have any questions, comments, if you want access to the web app, if you want mentorship, feel free to email me here and I'd be more than glad to reach out to you. So by the end of the video, again, we're imposing design constraints on the strains. We are going to start off with the mass of 1.6 for the composite laminate you see here applied to this cylindrical tube. We are going to end off with the minimum strain of negative 0.00585 for lamina 6. This example, I've done tutorials many times on this example, so I definitely recommend that you refer to one of my old YouTube videos describing this model in more detail. So in this video, I'm going to skip discussion on the objective and the design variables. I'm going to focus purely on the design constraint on the strains of the laminas. So we are going to impose a strain on lamina 1, 2, 3, 4, all 8 laminas in the laminate. And we are going to say that the minimum strain should be no less than negative 0.00613. Now let's go ahead and walk you through the process of doing that for MSC Nastran. I've already performed this analysis in Patran. I already have my PDF file. I've already constructed the design model complete with design variables and the design objective. All I need now is to define the statements for my design constraints. So here's my design model. Here are the old constraints I have from a previous practice run. I'll just go ahead and delete those, and now we'll take time to go ahead and walk you step by step on how to create new constraints for the strains of each lamina with the web app. Again, this web app is available in the more advanced training I provide. My email address is here. Definitely feel free to pause the video now, write the email address, and shoot me an email. I check the email address regularly, so I'll definitely get back to you as soon as possible. So let's go ahead and open the web app now. Once you're in the web app, click on Constraints to define your constraints. You'll see a long list initially displayed for you. Out of this list, search for strain, and there'll be a response type that says composite strain. So here, let's go ahead and type in strain. Or maybe, yes, the one we are looking for is strain in pcomp. This is the response type or the constraint you want to use. So let's go ahead and click on this one time to create one design constraint in our next table. I'm going to go through this relatively quickly since I've made a lot of comments regarding this in the last few videos. So here, we want to apply this constraint to element 64. This is going to be for lamina 1. And for our lower bound, we had a value of negative 0.00. Let me look at my optimization problem statement again. 0.00613. So let me go ahead and copy that and just paste it right here in this box. And then for the stress item code, this is available in the MSC Nastran Quick Reference Guide, Chapter 6. There's a section called Element Stress or Strain Item Codes. Go to this section and then start looking for the C quad 4 element type for composites specifically, and it'll say composite right underneath the C quad 4 label. Look for the item code corresponding to the normal 1 direction. Here I see that the normal 1 direction is corresponding to item code 3. So back in my web app, that is the item code I want to use in this box that says strain item code. So let's go ahead and type in 3 there. And that completes creation of one constraint for lamina 1. I want to apply this constraint to lamina 2, 3, 4, and all the way through 8. So let's go ahead and create 7 additional constraints. And just repeat the process that I just did. And this is being applied to only one element, so I'm typing in ELEM for the property type, and then I'm using 64 for the other elements here. And then the lower bound's the same for all the laminas, so I'll go ahead and use the same bound. And then for the stress item code, we're using 3, which corresponds to the normal 1 direction. And then we want to do this for lamina 1, 2, 3, 4, and so on until we get to lamina 8. So there we have it. That completes creation of our design constraints on the strains for each lamina. Let's go ahead and copy all of these new statements and paste these new statements in our design model. And now we are at the point where we can now perform our optimization. So let's go ahead and run this optimization now. So I will start MSC Nastran and point to this BDF file. Let's go ahead and perform the optimization. Again, full details on this example on defining the mass and design variables, that's in another YouTube video that's, I think, more than 20 or 30 minutes long. So feel free to view that video so you see this from the very moment you export your BDF from Patron to the final moment where you look at optimization results and produce a new BDF file with the new ply orientations and thicknesses. And in this video, again, we just focus on the process of imposing a design constraint on the strains of each lamina. And right now, as I'm speaking, MSC Nastran is performing the optimization. Let me go ahead and jump to the next slide and maybe start speaking about the results. Here on the left are the initial design results. So I started off at a mass of 1.6 lynches, and I'm expecting 0.16 lynches for the new design with new orientation angles, new thicknesses. And when I look at the strains in all of the laminas, I found that the smallest strain there is negative 0.00585 for lamina 6. And this is still within the constraint we define. So let's go ahead and look back and see if our optimization is complete by opening up the F06 file. At the very bottom of the file, let's go ahead and check and see if I have my message indicating a successful optimization here. That message is there. And we see that here in this column, we start off with the mass of 1.59 lynches and we end off at a mass of 0.159. Here are our new thickness value and ply orientation angles for the design variables. So this is exactly what I was expecting. So now let's go into more detail regarding the results. Here in this plot, bottom left-hand corner are the ply orientation angles after each design cycle. The initial analysis or initial design had ply angles of 85 and 60 degrees. You can see after the first design cycle, it actually modified some of the orientation angles. But here is the more significant thing that happened. On the right is the plot history of the thicknesses for each design cycle. After design cycle 1, the thickness went from 0.01 and it went down all the way to 0.001 inches. This limit actually is a limit on the ply thickness. We imposed a design variable limit that said the thickness cannot be anything less than 0.001. So you find that limit was hit here during the optimization process. Now, as I mentioned in many videos before, when you look at the normalized constraint history, and these numbers were extracted from a CSV file that was produced during the optimization, these numbers also correspond to these values in the table. Maximum value of constraint. So these normalized constraint values, each design cycle will have a design constraint that is the leader in the pack. It's the one that's the most in violation. Each design cycle will have a different dominating constraint. So for example, during the initial design, the strain 1 of laminate 8 was the leader in violating the design constraint. Strain 1 had a strain that was less than our lower bound, so that was influencing the design process for the first design cycle. Now, after design cycle 1, there is a new design, a new orientation angles and ply thicknesses, as we discussed in the previous slide with the new values after design cycle 1. For this new design, there could be a different design constraint that's dominating or that's has to be satisfied. So here, for example, after design cycle 1, sigma 1 of lamina 5, this was the constraint in most violations. So this dictated the next design cycle process to some extent, and so on and so on. A way you can tell which design constraint was being violated the most, and here let me go ahead and switch back to my F06 file. If you look at the summary after each design cycle, and here, for example, let's go ahead and look at the final analysis as one example. There's a section called Design Constraint on Responses. If you look for this double asterisk, and I don't know if I should be able to find it. Here, I did find it. This whole section corresponds to the normalized constraint values that you see in the value column. If you look through this column, one value or one row in particular has a double asterisk. This is the leader in the constraints. This is the constraint that's in most violation. And now if you look at the internal response ID, which is a 7, use that 7 and scroll down to a section called Responses in the Design Model. If you look in this section and look in the first column, internal ID, we're looking for the row marked 7, and that will be this row here. You can see that this corresponds to a response label R6. So this would be the R6 you find here. And this row was used to define the constraint for lamina 6. If we look a little further to the right, you see the lamina number here. You see the bounds imposed on this constraint. And here in the value column, you see the actual strain value for that result, which is negative 0.00585 and so on. And that's the one I have noted back in my PowerPoint. So negative 0.00585. And now let's go ahead and view these results in Patran just to quickly show this. This new result file that was created during the optimization process has the results for both the initial and the final design. Once I import these results to Patran, I'll go ahead and show you what the strains look like for element 64 ply 6. You notice this one's the closest to violating the lower bound of negative 0.006. So let me go ahead and show Patran right now. Let's go ahead and view our results, and I think I'll show you the tensor of the strains. So here I've selected D3, which corresponds to design cycle 3, the last design cycle in our optimization process. Let's go ahead and select element 64. And let's go ahead and plot this tensor. And so here's what the tensor looks like for ply 8. Let's go ahead and switch this to ply 6. Perfect. So here, let me zoom in a little more. Maybe I should switch the scaling of this so it's a little easier on the eyes. You can see that in the one direction, we finally have, or we are looking at the, how do I say, the strain in the one direction, which is now negative 0.005. And to begin with, the strain at the initial design for lamina 6 was actually positive. So there you have it. That's how you impose a design constraint on the lamina strains. In my other videos, I described the process for imposing design constraints on failure index, strength ratio, and stresses in the one or two direction. As always, if you have any questions, my email address is at the bottom right hand corner. If you have any questions, comments, you can email me. You can leave a comment in the video description below. If you want access to the web app that makes the process of creating your optimization models faster, also email me. I'd be more than glad to work with you on getting you set up with that. Thank you for watching.